Finally, let's take a look at frequency. Frequency is going to be a function that you'll implement in helpers.c that takes as input a string, which we'll call note, and output an integer. So what is that note going to look like? Well, the note is just going to be a string that might be something like A#4, for example, a note, possibly an accidental, and then an octave number. But if there is no accidental, that note might just be A4, for instance. So what are you going to do with that note? Well, first, you're going to parse the string and figure out its note and its octave. So in the case of the string A#4, the note is A#, and the octave is octave number 4. But you'll need to figure out where in the string the note part is and where in the string the octave part is. Next, you'll calculate the frequency of the note in the given octave. In music, we say that every note has a different frequency, a different pitch that makes each note sound different from one another. And those frequencies are generally represented in a unit called hertz. More on that in just a moment. And finally, you'll return that frequency as an integer value in hertz back to the user. So how do we figure out what the frequency is of any given note? Well, the world is sort of standardized upon the idea that the note A4, or A in the fourth octave, will have a frequency of 440 hertz. So that's something that you can take for granted. If the user passes in A4 into your function, then the output is just going to be 440 as the return value. But what if the note isn't A4 and it's some other note? Well, generally when we're talking about frequency, we can follow these rules. If A4 is 440 hertz, then for every semitone up that we move, remembering that a semitone is just a movement of one key on the piano keyboard, for every semitone up we move, we're going to multiply the frequency by 2 to the power of 1/12. And likewise, for every semitone down we move, we're going to divide the frequency by 2 to the power of 1/12. Let's take a look at what that actually looks like from the perspective of the piano keyboard. So we know that A4 is 440 hertz, and that's just a standard. But what about one semitone up from it, A#4, or equivalently B-flat4? Well, all we're going to do there is remember that when we move up one semitone, we take the frequency and we multiply it by 2 to the power of 1/12. So if we take 440 and multiply it by 2 to the power of 1/12, we get about 466 hertz as the frequency for A#4. What about one more semitone up to B4, the next semitone after A#4? Well, we'll take 466 approximately and multiply that by 2 to the power of 1/12, which is really the same thing as taking 440 and multiplying it by 2 to the power of 1/12 twice, which is also the same thing as taking 440 and multiplying it to 2 to the power of 2/12, which would come out to be about 494 hertz. Likewise, if we were to move one semitone up from B4 to C5, remembering that new octaves always start with C, we get 440 times 2 to the 3/12, which is about 523 hertz, and so on and so forth. The next note is going to be multiplying 440 by 2 to the 4/12, then 5/12, 6, 7, 8, 9, 10, 11. And finally, when we hit A5, exactly one octave above A4, we've now moved 12 semitones away, or a full octave, and what we get is 440 times 2 to the 12/12, which is just 2 to the 1, or 2, and when we multiply 440 by 2, we get 880. So notice here that A5, exactly one octave above A4, all we had to do is take A4's frequency, 440 hertz, and multiply it by 2 to get 880 hertz for A5. So what does this actually mean in terms of frequency? Well, if A4 is 440 hertz, then anytime we want to take a note and go up an octave, we multiply it by 2 to the 12/12, which is just the same thing as multiplying it by 2. And likewise, to go down an octave, we just take the frequency and divide it by 2. And this doesn't just apply to A4. Given any note, if you want to move it up an octave, all you have to do is take its frequency and multiply it by 2. And to move it down an octave, you just take its frequency and divide it by 2. So now let's think about how we're going to take a note, represented as a string, and figure out what the letter of the note is, what its accidental is, and what its octave is. So, if we have a note represented as a string, That could take any form of A4 to B flat 4 to C sharp 5 or anything of the like. But we know that the note is going to be a string, and the first character of the note is always going to be the letter of the note, either A or B or C, D, E, F, or G. That much we can rely on. The second character of the note depends a little bit upon what note it is. If the note is a sharp or flat and has an accidental as a result, then the second character of that note string is going to be that accidental. For example, in the string A sharp 5, the second character is that sharp symbol. On the other hand, if there is no sharp or flat, as we might call a natural note, then the second character isn't going to be the sharp or flat symbol, but it's going to be the octave symbol. So for instance, if we had the note C4, where there is no sharp or flat, C is still the first character, the letter of the note that we want, but the second character is going to be the octave, octave number 4. Finally, if there was an accidental, sharp or flat, we still need to figure out what octave it's in. So if there was an accidental, then the third character of the string is going to be the octave. So in the case of a note like B flat 4, B is the first character, and that's the letter of the note. Flat, or represented by the lowercase b symbol, is the accidental. That's what's going to show up as the second character in the string. And finally, the third character of the string is going to be the octave number. And so now that we understand how to actually represent a note, let's walk through the steps of how we're going to go from taking an arbitrary note, that could be any note, and turning it into an actual frequency. But let's take it step by step. The first thing that you'll probably want to do is to implement different octaves of A. You know that for A4, you can just return the number 440, because we've set that that is the number of hertz that represents the note A4. But what about other octaves of just the note A, like A3 or A2 or A5 or A6? Well, we know that to change the octave, we just need to multiply or divide by some power of 2. To get from A4 to A5, we take 440 and multiply it by 2. To get from A4 to A6, we take 440 and multiply it by 2 twice, or multiply it by 4. Likewise, to go from A4 to A3, we'll have to divide by 2 to get 220 hertz for A3. And so, we can use multiplication or division by some power of 2 to be able to figure out what the frequency of some different octave of A is going to be. And finally, be sure that when you do this math, you're rounding any decimals that you get to the nearest integer. So, now that we've got different octaves of A, let's think about accidentals, sharps or flats that might modify A, and how we're going to adjust for those frequencies as well. So, step 2 is going to be supporting a sharp and a flat. Well, we know that to make a note sharp, since a sharp just means exactly one semitone ahead of the previous note, all we have to do is multiply the original frequency by 2 to the power of 1 over 12th. Remembering that in order to get from one frequency to the frequency exactly one semitone above it, we just multiply by this 2 to the 1 over 12. Likewise, to make a note flat, we'll do the opposite. Divide the frequency by 2 to the 1 over 12. So now think about, if we have A, and A4 is represented by 440 hertz, and we want to represent A sharp 4, for example, all we need to do is take the frequency 440 and multiply it by 2 to the 1 over 12. And likewise, for A flat, we would take the frequency 440 and divide it by 2 to the 1 over 12. But as you do this, also make sure to be able to support A sharp and A flat in multiple different octaves. Sure, A sharp 4 is just A4's 440 hertz multiplied by 2 to the 1 over 12, but what about A sharp 5 or A sharp 6? Well, if you remember that in order to go up an octave, you just multiply the frequency by 2, and to go down an octave, you just divide the frequency by 2, then if you know what A sharp 4 is, all you need to do is multiply that frequency by 2 in order to get A sharp 5. So you might think about first adjusting for sharps or flats, and then adjusting for different octaves. Or alternatively, you could do it the other way around. First, adjust for the octave by multiplying or dividing by some power of 2, and then adjusting for sharp and flat. And finally, once we've supported A sharp, and A flat, the last step is going to be to support all different kinds of notes, where we'll use A as our starting point and figure out how many semitones away various notes are. And if you take a look at a piano keyboard, you should be able to figure this out. If you remember which note has which letter, you should be able to calculate how many semitones away B is from A, how many semitones C is away from A, and as well for all of the other notes that appear on the piano keyboard. An important thing to remember is that octaves start at C. In other words, C5 is one semitone above B4. This becomes clear if you take a look at a picture of the piano that represents all of the different notes and what octaves they belong to, where you'll notice that the fourth octave ranges from C4 all the way up to B4, but as soon as we move from B4 to the note one semitone after that, we arrive at C5, which is the beginning of the fifth octave. So while it may seem a little bit counterintuitive, A4 and B4 are actually higher notes than C4, even though C comes later in the alphabet, because C marks the start of the octave. And so, bearing in mind which notes belong to which octaves and when new octaves are starting can help you out when it comes to computing the frequency. So ultimately, the logic that you're going to want to follow is to first figure out what the string actually represents, what the letter of the note is, what accidental it has, and what octave it has. Then, using A4 as your baseline, where you know that A4 is equal to 440 hertz, you can adjust. Anytime you move up a semitone, multiply by 2 to the power of 1/12. Anytime you move down a semitone, divide by 2 to the power of 1/12. And if you ever want to jump a full octave, remember that to go up an octave, you just take a frequency and multiply it by 2. And anytime you want to go down an octave, you just take the frequency and you divide it by 2. At the end, you'll likely end up with a floating point number with digits after the decimal point, but remember that the frequency function is supposed to return an integer. So once again, make sure you're rounding your number to the nearest integer in order to make sure that your output matches the desired frequency level. So those are the steps to figuring out frequency, after which point you should be able to hear songs and listen to them based on the functions that you've implemented inside of helpers.c. On that note, I'll leave you to it. Good luck. My name is Brian, and this was music.